Everything in the universe is made from matter, from the smallest rock to the largest star. And all the matter there will ever be was created from the pure energy of the Big Bang. Einstein's equation, E equals mc squared, says that energy transforms into matter. But it was just a theory. Today, science is able to test that theory. This is CERN in Switzerland, home to the world's largest machine. It's the size of a city and engineered to recreate the conditions millionths of a second after the Big Bang.
If we want to probe ever smaller scales, paradoxically, we need an ever bigger machine. There's just no other way of doing it. So big machines means small physics, means early times, and therefore getting closer and closer to the origin of the universe itself.
This monster machine is called a collider. It's designed to take us back to those first fractions of a second after the Big Bang. It's a 3.8-meter wide, concrete-lined, circular tunnel, 27 kilometers around. The collider makes tiny particles of matter smash into each other at almost the speed of light. For a split second, those collisions generate turbocharged energy, similar to the explosive force of the Big Bang. And then that pure energy, briefly, transforms into matter, just like it did nearly 14 billion years ago. But this huge machine needs an enormous detector to see these collisions.
This detector is 5 stories tall and weighs over 7,000 tons. And 7,000 tons, to give you a sense of perspective, is the weight of the Eiffel Tower.
But as big as it is, it can't see the actual particles of new matter. They're only present for just a split second and move so fast, it can only record their trails.
There's a lot of energy in these particles. They move very, very quickly, and so you need a very large amount of detector in order to be able to map the path of these particles very precisely. So the detector is so big because you need better resolution. It works exactly the same as a camera. The more pixels you have, the better the picture. It's exactly the same here. We just have a 5-story camera.
Scientists hope that it'll reveal just how energy transforms into matter. But not just any matter. The type of matter that emerged nearly 14 billion years ago, at the dawn of time itself. But the dawn of time was a critical moment in the birth of the universe, because pure energy also produced one of the most dangerous things in the universe: antimatter.
Antimatter is the mirror image of ordinary matter. However, matter has one charge, and antimatter has the opposite charge. If there was an anti-me made out of antimatter, that person in principle could look exactly like me. Same personality quirks, same everything, except of course when I decide to shake his hand. At that point, we both would blow ourselves to smithereens in a gigantic nuclear explosion.
Matter with a positive charge clashes with antimatter with a negative charge. The fate of the universe hangs in the balance of this epic battle. Equal amounts of matter and antimatter will cancel each other out, and it's not good.
A universe with equal amounts of matter and antimatter is equivalent to a universe with no matter at all, because the matter and antimatter will annihilate back into pure radiation. And there'll be nothing interesting, no stars and galaxies and people in between.
It was a cosmic battle, and the side with the most forces would win. It was very close, but there was one winner.
For every billion particles of antimatter, there were 1,000,001,001 particles of matter. That was the moment of creation. The one extra particle of matter in each little volume survives enough to form all the matter we see in the stars and galaxies today.
One in a billion might not sound like much, but it's enough to build a universe.
We're the leftovers. So believe it or not, everything you see around you, the atoms of your body, the atoms of the stars, are nothing but leftovers. Leftovers from this ancient collision between matter and antimatter.
Could antimatter still exist?
In the laboratory today, we have created anti-atoms, anti-electrons going around anti-protons to create anti-hydrogen.
Antimatter by itself is quite harmless. It's only when it comes into contact with matter that the fireworks start. Give or take a couple of Planck times, the universe is nearly a second old, and still a very strange place. But matter has won the battle with antimatter. And now it's time to build the universe. It's still extremely hot and expanding incredibly fast.
When the universe was a second old, the particles in it were very different than the particles we see today. There were no atoms. Nothing that we recognize in the room around us today yet existed.
However, now all that begins to change. Temperatures continue to cool, and as the primitive particles keep slowing down, they start bonding together to form the atoms of the first elements. The first one to form is hydrogen. Then, over the next 3 minutes, the universe begins to create two more elements, helium and lithium.
It's really amazing to think about that in a period of 3 minutes, which is, say, the length of an average news story on television, the universe went from the Big Bang all the way to forming the light elements that would be the building blocks of everything we see. In that short period, we went from the creation of a universe to ultimately the creation of matter. We went from a universe that was infinitely small to a universe that was light years in size. In the first 3 minutes, essentially everything interesting that was going to happen in the universe happened.
However, you wouldn't have been able to see it.
When we look at the night sky, we can see literally billions of years into the past, and we think it's always been that way. Nope, not true. 380,000 years after the Big Bang, that's when the universe began to become transparent. But before then, it was milky.
There is a dark, milky soup of loose electrons. The young universe has to cool down enough for the electrons to slow down and stick to new atoms. It took a long time for all the hydrogen, helium, and lithium atoms in the universe to form. Scientists calculate it took 380,000 years for the electrons to slow down enough so that the universe could start mass-producing atoms. When that happens, the milky fog clears. The first light escapes and races across the universe. Nearly 14 billion years later, two young scientists in New Jersey pick it up by accident. In 1964, Arno Penzias and Robert Wilson were mapping radio signals across our galaxy. Everywhere they searched, they picked up a strange background hum. They first suspected their equipment. Pigeon droppings were on the antenna. Maybe these were causing the strange signal. But after cleaning the antenna, the mysterious hum remained.
Penzias delivered a talk at Princeton University. And according to lore, one person in the back said, either you have discovered the effects of bird droppings or the creation of the universe.
It was, in fact, the moment of creation, nearly 14 billion years ago, when those first atoms got their electrons. That's the moment when the Milky Cloud clears and a new universe comes into view for the first time. To capture better images of this critical event, NASA launched the Cosmic Observer Background Explorer satellite, or COBE. They pointed it out into space where it took the temperature of the universe. By measuring differences in temperature across space, they created the first map of our early universe.
We got gorgeous pictures, baby pictures of the infant universe when it was 380,000 years of age. But there were problems with it. The picture was very fuzzy. The COBE results were simply not good enough.
So NASA launched an even more advanced satellite, WMAP, the Wilkinson Microwave Anisotropy Probe. In 2001, David Spergel was part of the team searching for a clearer image of the early universe.
It was exciting to go to the Cape. It was one of these moments where we're sitting there watching this. I was there with my family, watching the rocket go off. And it was very exciting when within about a day, we were able to get our first signal from the satellite and know it was working and working properly.
This is the most detailed picture of the early universe ever taken. Just 380,000 years after the Big Bang. The red and yellow areas are warmer, the blue and green regions cooler. And those temperature differences are clues to the future structure of the universe.
We see tiny variations in temperature. Those tiny variations in temperature reflect small variations in density. This region has more matter, this region has less matter.
Like a blueprint for the construction of our universe, this image shows us where there's more matter and where there's less. Regions with no matter will become empty space. Areas with denser matter will become the construction sites of galaxies, stars, and planets.
These are the fluctuations that will grow to form galaxies. So if it wasn't for those little density fluctuations, you and I would not be here today.
Believe it or not, everything you see around you, the galaxies, the stars, even the atoms of your body, have a predecessor in the Big Bang itself. Our galaxy was a ripple, a tiny ripple on the surface of the Big Bang as it exploded out. And these tiny ripples gave birth to all the galactic clusters and things that we see around us.
Our universe is now 380,000 years old, and trillions of kilometers across. Clouds of hydrogen and helium gas float through space. It'll take another 200 million years before those gases create the first stars.
These first stars ignited the universe into what must have been the most amazing firework. The universe went from the Dark Ages to an age of splendor when the first stars illuminated the gas and the universe began to glow in majestic fashion. I wish I'd been there.
It was like Christmas tree lights turning on. The universe began to light up in all directions until you formed the beautiful mosaic we now see today.
More and more stars begin to shine. 1 billion years after the Big Bang, the first galaxy forms. Over the next 8 billion years, many more take shape. Then, about 5 billion years ago, in a quiet corner of one of those galaxies, gravity begins to draw in dust and gas. Gradually, they clump together and give birth to a star, our sun. "9 billion years after the Big Bang, our tiny solar system springs to life, and with it, planet Earth. Everything there is exists because of the Big Bang, and it's still going on. Our universe is still expanding. But it won't just keep going forever. Our universe had a beginning, and it will also have an end.